Hello, and welcome to Sleepy Starlight Channel. I'm so glad you're here tonight. Maybe your day was long, or maybe you're simply looking for a calm voice to help you unwind and drift into sleep. Tonight, we'll take a gentle journey where science becomes a story and curiosity leads us softly into dreams. Let us begin our journey with the star that gave us everything, the sun, the quiet engine of life, the golden heart of our solar system. It burns not in chaos, but in harmony. For more than 4.5 billion years, it has risen faithfully, painting the earth with warmth and light. And yet, hidden within that steady glow is a promise, or perhaps a warning. For one day, this same light will be the force that ends our world. The sun seems eternal, but it is not. Like all stars, it was born, it lives, and it will die. Its calm face hides a storm of unimaginable power, nuclear reactions so fierce that every second it releases more energy than humanity has ever produced in all of history. That energy travels outward, crossing 93 million miles of empty space before it touches Earth, giving us day, seasons, oceans, weather, and the fragile bloom of life. But every moment of radiance comes at a cost. The sun consumes itself. Deep in its core, hydrogen atoms are fused into helium in a process that slowly changes its balance. With each passing eon, its fuel diminishes. The glow that nurtures Earth is also the slow unraveling of the sun's own body. To understand how it will destroy our planet, we must first understand how it lives. The sun is not fire in the usual sense. It is plasma, matter so hot that atoms are stripped of their electrons, forming a fluid of charged particles. Inside, gravity pulls inward while radiation pushes outward, locked in a perfect tension. That balance keeps the star stable, neither collapsing nor exploding. For billions of years, this harmony has endured, but it is not infinite. At the center, where temperatures reach 15 million degrees Celsius, 4 hydrogen nuclei merge into one helium nucleus, releasing light and heat. This fusion is slow but relentless, and the core where it happens is only about a quarter of the sun's total size. Above it lies a vast radiative zone where light struggles to escape, bouncing from atom to atom in a journey that can take hundreds of thousands of years before it finally reaches the surface. From there, it streams freely into space, illuminating the planets. Every photon of sunlight that warms your skin began its life long before humanity existed. Each carries within it the memory of the sun's deep interior, a message written in heat and time. But that same process that creates light also builds up a silent pressure in the core. As hydrogen burns away, helium accumulates, changing the sun's internal structure. Over time, the fusion slows, gravity tightens its grip, and the star begins to change. Already, the sun is brighter than it was when the Earth first formed. 4 billion years ago, its light was weaker by nearly 30%. Yet even then, Earth was warm enough for oceans to form. Scientists call this mystery the faint young sun paradox, how a dimmer sun could have sustained liquid water. The answer lies in our atmosphere. Ancient Earth was rich in greenhouse gases like carbon dioxide and methane, trapping more heat than it does today. As the sun brightened, those gases declined, balancing the climate. It was a delicate dance between light and air, one that cannot last forever. Every billion years, the sun's output increases by about 10%. To us, that seems small, but to a planet, it means everything. In another billion years, Earth will receive too much light. The oceans will begin to evaporate. The sky will thicken with water vapor, amplifying the heat even more. The cycle will feed on itself. The same greenhouse effect that once protected the planet will become its undoing. Before that distant catastrophe, the sun will remain stable, a perfect example of what astronomers call a main sequence star. This phase, the long middle age of stellar life, is when hydrogen fusion proceeds smoothly, keeping the star in balance. For the sun, that main sequence will last about 10 billion years. We are roughly halfway through. That might sound like comfort, but in cosmic terms, it means the clock is ticking. Deep inside, the helium core is growing, compressing under gravity. As it does, the outer layers of the sun slowly expand. Over millions of years, the balance between pressure and gravity shifts. The sun becomes larger, brighter, and more unstable. It will not stay the same forever. When we look at it now, we see a disk of blinding light, but beneath that calm glow lies movement on an immense scale. The surface boils with convection cells the size of continents, hot plasma rising and falling in endless motion. Magnetic fields twist and snap, creating sunspots, dark regions cooler than their surroundings, and solar flares that erupt into space with the force of billions of atomic bombs. These storms send waves of radiation and charged particles racing toward the planets. When they reach Earth, they can disturb satellites, disrupt power grids, and paint the sky with auroras. The sun's activity follows cycles, repeating every 11 years. At the peak, called solar maximum, flares and storms are frequent. At the minimum, the surface quiets, though the core remains unchanged. This heartbeat of magnetism has pulsed since the dawn of the solar system, shaping not only our space environment, but perhaps even Earth's climate across the ages. Despite its turbulence, the sun is remarkably stable compared to other stars. It does not flare violently like red dwarfs or collapse suddenly like supergiants. Its steadiness has been the foundation of life, but that stability will not last forever. When the hydrogen in its core runs out, gravity will begin to win. The sun will contract, heating up its outer layers, forcing new reactions to ignite in shells around the core. And that will mark the beginning of the end. In those future days, the sun will grow, slowly at first, then dramatically. Its surface will swell outward, its color shifting from golden white to deep orange-red. Mercury will be consumed entirely. Venus will be stripped bare, its atmosphere blown into space. And Earth, our fragile world, will be scorched. The seas will boil away, the rocks will glow, the sky will burn. But this destruction is not senseless. It is the natural evolution of stars like ours. The death of one world ensures the birth of others. The sun's outer layers, once ejected, will drift into space, carrying with them the carbon, oxygen, and other elements forged inside its furnace. These materials will seed new nebulae, from which new stars and planets will form. The end of the sun is not an end at all, but a transformation, one life giving way to another. For now, though, we are living in the golden age, the calm before the slow unraveling. Every sunrise we see is a miracle of balance, the brief period in which a star's fire and a planet's breath coexist perfectly. The sun does not rage or rest, it simply endures, burning quietly, holding the memory of its birth and the promise of its death. In the next part, we will travel deeper into that story, through the future epochs of the sun, the swelling of the red giant, the vanishing of the planets, and the transformation of our solar system into a place of silence and ash. The red giant phase is the sun's grand transformation, a final burning bloom before silence. It will begin quietly, invisible to any short-lived creature. But over millions of years, the change will accelerate until the calm yellow star that nourished life becomes something enormous, ancient, and unrecognizable. When the sun exhausts the hydrogen in its core, fusion will cease there. Without that inner fire pushing outward, gravity will win for a time. The core will contract, growing smaller and denser. As it collapses, its temperature will rise to unimaginable levels, over 100 million degrees. This heat will ignite new layers of fusion around the core where hydrogen still remains. The reaction will move outward in waves, like fire spreading through rings of dry wood. These new layers of fusion will generate enormous energy, forcing the outer shell of the sun to swell outward. The star's radius will grow, first slowly, then rapidly, expanding hundreds of times its original size. From the Earth's point of view, the sun will no longer be a small, blinding circle in the sky, but a vast red disk that dominates the heavens. Its color will deepen to orange, then to crimson, as its surface cools slightly, even while its total brightness increases. The sun will enter the true red giant phase. Its outer layers will balloon into space, becoming thin and fragile, glowing like mist. The temperature at its visible surface will drop, giving it that deep red hue, but the energy pouring out will be many times greater than today. For the inner planets, this change will be catastrophic. Mercury, closest to the sun, will vanish first. Its rocky surface will liquefy, its metal core will melt, and within weeks it will be drawn into the expanding atmosphere of the star. Venus will follow, its thick clouds of acid vaporized, its surface engulfed in a furnace of hydrogen plasma. And Earth, our world, will be next. At first, the oceans will boil away entirely, leaving dry basins of salt and stone. The atmosphere will thicken with steam and carbon dioxide, creating heat beyond comprehension. The surface will glow dull red, mountains melting into rivers of magma. The crust will begin to crack and shift, releasing new waves of volcanic fire, but even that will be brief. Eventually, as the sun's radius continues to grow, Earth's orbit will no longer protect it. There is a question, a small uncertainty that fascinates astronomers. Will the Earth be swallowed, or will it survive just beyond the sun's swollen edge? The answer depends on the balance of forces between expansion and loss of mass. As the sun grows, it will shed material into space in a powerful solar wind, reducing its gravity. This may allow Earth to drift outward slightly, escaping total engulfment. But if friction with the sun's outer layers slows its orbit, our planet will spiral inward, consumed in fire. If Earth survives, it will not do so in any recognizable form. The surface will be molten, the atmosphere gone. The moon will likely be stripped from orbit or crash into the planet. The entire solar system will become a landscape of ruin. Mercury and Venus gone, Earth a glowing ember, Mars scorched and lifeless, its frozen poles evaporated into space. The sun's expansion will reach its peak, its surface extending perhaps beyond the orbit of Earth itself. The star will appear enormous and dim to a distant observer, glowing like a great red pearl against the darkness. Its outer layers will pulse and shiver, shedding vast clouds of gas and dust into the void. From far away, from the edge of the solar system, perhaps from the orbit of Pluto, the spectacle would be beautiful beyond words. A red sphere surrounded by halos of glowing material, its light reflecting off distant icy moons. The solar system will have become a work of art in destruction, a cosmic flower opening in slow motion. Inside that beauty, the sun will be dying. Each pulse of brightness will carry away more of its mass, blown outward in solar wind thousands of times stronger than today's. The star will lose billions of tons of material each second. Great loops of plasma, millions of kilometers long, will arc into space and drift away, like petals torn from a burning rose. This process may last for hundreds of millions of years. The sun will swell and shrink in cycles, each time throwing off more of its substance. Around it, a shell of glowing gas will form, the early beginnings of what astronomers call a planetary nebula. This shell will expand outward, lighting up as ultraviolet radiation from the hot core strikes it. What remains of the sun will illuminate its own ashes. For the distant future observers, perhaps machines orbiting Saturn or alien astronomers from another star, our sun will appear as a luminous red orb wrapped in clouds of light. The planets will be ghosts, their orbits shifting as the sun loses mass. The inner solar system will be a hollow region filled with drifting dust, fragments of worlds long gone. And yet, not all will be lost. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will survive. The sun's gravity will weaken, and their orbits will drift farther outward, but they will remain. Their moons, frozen and scarred, may even find new balance in this transformed system. Some icy moons, warmed by the red giant's glow, could briefly host liquid water. For a short, miraculous span, tiny seas might form on worlds far from the dying sun. When the red giant phase finally ends, the sun will cast off its outer layers entirely. What remains will be its heart, a dense, brilliant core about the size of Earth, but containing half the sun's original mass. This is the white dwarf stage, the final ember of our star. The nebula surrounding it will glow for tens of thousands of years, a cosmic halo of color and light, before fading into darkness. The red giant's end will mark the true death of the Earth. Whether swallowed or scorched, our planet's matter will join the dust of the solar system, drifting outward into interstellar space. One day, those same atoms may find themselves in a new star, a new world, a new life. The death of the sun, then, is not a final annihilation, but a transformation. Stars die so that new stars may be born. Worlds burn so that new ones may arise from their ashes. Even destruction is part of creation, a slow recycling of matter and light. When we look at the sun today, we see only warmth and comfort, but within its glow lies the seed of its own ending. Its fire is not infinite, only long. It will burn for billions of years yet, but its destiny is already written in its core. In the next part, we will journey even further into that destiny, to the moment the red giant collapses into a white dwarf and the solar system grows cold, silent, and eternal. After the long age of fire, the sun will grow quiet. Its swollen red body, once vast enough to swallow worlds, will begin to loosen and fall apart. The outer layers will drift away, glowing for a time like the petals of a burning flower before dissolving into the cold. What remains will be the core, the sun's heart laid bare, small, brilliant, and impossibly dense. This remnant is called a white dwarf. It will shine with a ghostly blue-white light, not from fusion, but from memory, from the stored heat of its collapse. The white dwarf will be about the size of Earth, yet still contain nearly half of the sun's original mass. A teaspoon of its matter would weigh tons. Gravity there is so strong that the surface is smooth, compressed to a density no rock could endure. When the red giant's outer layers drift away, they will form a planetary nebula, though the name is misleading. It has nothing to do with planets. Instead, it is a shell of glowing gas, expanding outward like a luminous bubble. Ultraviolet radiation from the hot white core will illuminate it, creating swirls of color, greens, reds, blues, as atoms are ionized and recombine. For tens of thousands of years, this nebula will shine in space, visible from light years away as a delicate halo of fading light. Astronomers in distant galaxies might someday see it and know, a star once lived here and it has reached its end. Within that nebula, scattered fragments of the solar system will drift. Dust from Mercury and Venus, vaporized rock from Earth, frozen shards of Mars, all will become part of the expanding cloud. Comets and asteroids will wander through the remnants, colliding slowly, reshaping the debris into new forms. For a time, faint echoes of the old system will persist, a ring of dust around a dying light. The white dwarf will no longer burn hydrogen or helium. Fusion will be over. Instead, it will cool, slowly radiating away the heat trapped inside. At first, it will be brilliant, a white point brighter than most stars. But over billions of years, it will fade, glowing dimmer and dimmer until it becomes invisible to the eye. Around it, the surviving outer planets will continue to orbit, ghostly guardians of a vanished world. Jupiter and Saturn will circle their star from afar, their immense size unchanged, but their atmospheres cold and still. Their moons will be silent spheres of ice. Pluto and the scattered Kuiper Belt objects will drift in near total darkness, illuminated only faintly by the white dwarf's dying glow. The solar system, once alive with light, will become a museum of motion and memory. Planets circling a relic, comets tracing arcs through frozen space. No warmth will reach them, no light will nourish them. Only gravity will bind them, holding the ghosts of the planets in their eternal paths. If one could stand on the surface of that white dwarf, though no human could survive the gravity, the view would be haunting. The nebula would stretch across the sky like a ring of luminous smoke. Its colors would shift slowly as it thinned, fading into the endless black. The white dwarf's own light would be pure, sharp, and unwavering, its heat enough to melt diamond, though its fire was long gone. The transformation from red giant to white dwarf is the last act of the sun's stellar life. It will have taken billions of years to unfold, each stage as inevitable as the next. From birth in a nebula, to youth as a stable star, to maturity as the giver of life, and finally to death as a relic of its former brilliance. But even in this quiet end, there is continuity. The material shed into space will mix with interstellar gas, seeding the galaxy with heavier elements: carbon, oxygen, nitrogen, iron. These are the ingredients of worlds and of life. In some distant corner of the Milky Way, those same atoms may someday gather again, forming new stars, new planets, and perhaps new beings who look up and wonder about the light that made them. The white dwarf sun will cool slowly, so slowly that even after 10 billion years, it will still glow faintly. Eventually, after unimaginable spans of time, it will fade into a black dwarf, a star that has lost all visible light. At that point, the solar system will be truly dark. Time beyond that becomes difficult to imagine. The orbits of the surviving planets will decay under tiny gravitational influences. Some may drift away entirely, captured by passing stars. Others may remain, circling forever around their dark parent, like memories that refuse to fade. The galaxy itself will continue, indifferent and beautiful. Other stars will live and die, other worlds will bloom and burn. The remnants of the sun will be just one among countless others, a grain of ash in a vast cosmic sea. And yet, from a cosmic perspective, this is not a tragedy. The death of the sun is part of the cycle that made us possible. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the deaths of earlier stars. Their endings became our beginnings. In time, the sun will return the favor, scattering its matter into the galaxy, where it may again give rise to new life. In this way, death in the cosmos is never waste. It is renewal. The sun will not destroy Earth merely to end it, but to recycle it, to return its elements to the universe, to make space for what comes next. Even long after the last glimmer fades, the echo of its existence will remain. Its light, traveling outward, will still be crossing distant galaxies long after the solar system is gone. Somewhere, 1 billion light years away, a faint photon from our sun will still be flying, carrying with it the memory of this place, this moment, this brief spark of life. In the next part, we will step back from the end and trace how this entire story began, how the sun's life was born from dust, how it ignited, and how its long, quiet stability made everything on Earth possible. Before understanding how it will die, we must remember how it first came to shine. Before the sun could die, it had to be born. Its story began more than 4.5 billion years ago, long before there was an Earth, a moon, or even the faintest whisper of life. In a quiet arm of the Milky Way, within a vast cloud of hydrogen and dust, gravity began its slow work, a patient artist sculpting the future from formlessness. The cloud itself was ancient, the remnant of stars that had died long before. Supernovae had filled it with heavy elements, oxygen, carbon, silicon, iron, the raw materials of planets and living things. But for millions of years, that cloud remained cold and dark, drifting in silence. Then, perhaps disturbed by a nearby explosion or the passing of a spiral arm of the galaxy, it began to collapse inward. As gravity drew matter together, the center of the cloud grew denser and hotter. It spun faster, flattening into a disk, a whirlpool of gas and dust. At the center, a knot of material grew, pulling in more and more mass. Pressure built, temperature rose. Eventually, at about 15 million degrees Celsius, hydrogen atoms began to fuse into helium. Energy was released. A new star ignited. The sun was born. Its light, at first dim and unsteady, soon stabilized. The balance between gravity pulling inward and fusion pushing outward reached harmony. Around the newborn star, the leftover gas and dust in the disk began to clump together. Tiny grains collided and stuck, forming pebbles, then rocks, then planetesimals, the building blocks of planets. Over time, these bodies grew larger, their collisions violent and frequent, their heat melting rock and metal. From this chaos, the planets took shape. Closer to the sun, where heat was intense, lighter materials like water and gas were driven away, leaving behind the rocky worlds, Mercury, Venus, Earth, and Mars. Farther out, where it was colder, ices could survive, and giant planets of gas and frozen elements formed: Jupiter, Saturn, Uranus, and Neptune. The solar system was born from violence, yet balanced by the quiet glow of the sun at its heart. For hundreds of millions of years, the young sun was fierce. It shone brighter and more erratically than today, sending out solar winds strong enough to strip atmospheres from unprotected worlds. Yet this same energy shaped Earth into what it would become. It evaporated the last gases from the inner disk, allowing the planet to cool, oceans to condense, and an atmosphere to form. Somewhere within those early oceans, chemistry became life. Sunlight split molecules, powered reactions, and fed the first primitive cells. The sun was both sculptor and sustainer, offering warmth and energy in just the right measure. Too much, and the seas would have boiled. Too little, and they would have frozen. Somehow, Earth found the perfect distance, the narrow, habitable zone where liquid water could persist. For billions of years, this fragile balance held. The sun burned steadily, fusing hydrogen into helium in its core, releasing energy that radiated outward and gave Earth its light. That steady glow defined every rhythm of life, the days, the seasons, the cycles of climate and growth. In time, plants evolved the ability to capture sunlight directly, photosynthesis. With that, the sun's energy began to shape not only landscapes, but living systems. It became the silent pulse within every leaf and every breath, transforming light into food, air, and life. The sun's light drove winds, carved rivers, raised clouds, and wrote the weather. It painted dawns and sunsets, gave warmth to deserts and jungles alike. Every heartbeat, every spark of thought, every flicker of movement on Earth has been powered by its photons. To live on this planet is to live by the sun. For most of its life, the sun has remained calm. It sits in what astronomers call the main sequence, a long, stable period when hydrogen fusion in the core perfectly balances gravity. This phase lasts billions of years. For our sun, it is roughly 10 billion in total, and we are about halfway through. But even in this stability, the sun is not static. Its energy output changes slightly over centuries, and its magnetic field weaves patterns of activity across its surface. Sunspots appear, darker, cooler regions shaped by twisted magnetic loops. Solar flares erupt, releasing bursts of radiation into space. These events, though small compared to the sun's total power, can influence Earth's weather, disrupt satellites, and paint the night sky with auroras. The sun's outer layers are restless, bubbling with convection, hot plasma rising, cooling, and sinking again in endless motion. Its atmosphere, the corona, stretches far into space, glowing faintly even when the surface seems still. From that corona, streams of charged particles flow outward in a constant solar wind. This invisible river reaches all the way to the edge of the solar system, shaping the boundaries of our cosmic home. It is this wind that protects Earth, too. It pushes away much of the cosmic radiation that would otherwise bombard us. The sun, though fierce, also shields us, a paradoxical guardian. Its storms can be violent, yet without them, the solar system would be less alive. The light that leaves the sun takes 8 minutes to reach Earth, traveling through 93 million miles of emptiness. It moves silently, bearing the warmth of a star that has burned for billions of years. Every sunrise is, in truth, ancient light arriving from the past, a memory of fusion deep within the core, transformed into color, heat, and life. To understand the sun's destruction, we must also understand its gift. It is the giver of time, of rhythm, of balance. It makes life possible, and in doing so, it writes the destiny of every world that circles it. The sun does not choose to destroy. It simply follows the laws written at its birth. Its end is not anger or punishment, but completion. Like all living things, it will burn its fuel, grow old, and change. The beauty of the cosmos lies in this cycle, creation and dissolution, each depending on the other. When we look at the sun today, we are seeing it in its prime. It burns steadily, its heart quiet and stable. But deep inside, change is already underway. The helium ash in its core is accumulating. The fuel is thinning. The clock of stars runs slow, but it never stops. In the next part, we will look more closely at that slow transformation, the physics of fusion, the hidden changes inside the sun's core, and how those invisible processes set the stage for everything that will come: expansion, death, and the end of Earth's age of light. Inside the heart of the sun, time moves differently. What looks from the outside like endless constancy, a golden, unwavering light, is, in truth, a symphony of motion. Beneath the visible surface, trillions of reactions occur every second. Hydrogen atoms collide and fuse into helium, releasing photons that will take thousands of years to reach the edge of the sun and only 8 minutes more to reach Earth. This process, nuclear fusion, is the very essence of the sun's life. It is delicate, balanced, and astonishingly slow. Each fusion reaction converts only a tiny fraction of mass into energy, but there are so many reactions happening simultaneously that the result is immense, about 400 million billion watts. That is the power output of the sun, steady and patient, pouring into space in every direction. The core where this happens is dense beyond imagination, more than 100 times the density of water. The temperature there is around 15 million degrees Celsius. At such extremes, matter exists not as atoms, but as plasma, a sea of charged particles stripped of their electrons. In this inferno, hydrogen nuclei, protons, move fast enough to overcome their natural repulsion and merge, forming helium. But fusion is not eternal. The sun has been burning hydrogen for nearly 5 billion years, and it will continue for about 5 billion more. Yet even now, subtle changes are unfolding in the core. Each time hydrogen fuses into helium, the balance shifts slightly. Helium is denser than hydrogen, so it sinks toward the center, forming a growing core of ash, inert material that no longer contributes to the energy flow. As this helium core builds up, the sun's energy output changes. To maintain equilibrium, the surrounding hydrogen-burning shell must heat up and fusion accelerates. The sun becomes gradually brighter, roughly 10% every billion years. It's a small change to us, but it will eventually transform Earth's climate beyond recognition. Already, this increase has been quietly influencing our planet's history. Hundreds of millions of years ago, when the sun was slightly dimmer, Earth's atmosphere held more greenhouse gases to trap warmth. Now, as the sun grows brighter, those gases have diminished, keeping temperatures relatively stable. But this balance cannot last forever. 1 billion years from now, sunlight will be too intense, and no amount of atmospheric adjustment will protect the planet. Within the sun itself, the story of aging continues. The layers above the core are in constant motion, hot plasma rising, cooling, and sinking in vast convection currents. Magnetic fields twist and snap within this turbulence, producing solar flares and sunspots. These events are small ripples compared to the sun's total life, but they reveal its restlessness. The surface we see, the photosphere, is merely the skin of an ocean far deeper and more complex. Every 11 years, the sun's magnetic field flips. North becomes south, and south becomes north. During this solar cycle, the number of sunspots and flares waxes and wanes, affecting Earth's space weather. Aurora lights dance at the poles, satellites feel the push of increased radiation, and cosmic rays are deflected or amplified. This rhythmic breathing of magnetism is the heartbeat of the star. Beneath that rhythm lies an unbroken process of transformation. Slowly, helium accumulates. The core contracts under gravity. The surrounding layers expand slightly to balance the pressure. Each adjustment is small, each step stable, but over billions of years, they add up to change. If we could look inside the sun, we would see zones of subtle difference. The inner core, where fusion occurs, is surrounded by the radiative zone, a region where energy moves outward not by motion, but by light. Photons here scatter endlessly, absorbed and re-emitted by atoms. A single photon may take hundreds of thousands of years to escape. Above that lies the convective zone, where energy finally moves by movement, columns of hot plasma rising and falling in great cellular patterns, like slow boiling water. At the surface, the photosphere glows at about 5,500 degrees Celsius. Above it, the corona, the outer atmosphere, reaches millions of degrees, its heat driven by magnetic waves we still struggle to understand. From this corona, the solar wind flows outward, a stream of charged particles that fills the solar system and shapes the delicate boundary known as the heliosphere. The sun's wind creates a bubble in space, protecting planets from much of the interstellar radiation beyond. At the outer edge of this bubble lies the heliopause, where the solar wind slows and mingles with the galactic medium. In this way, the sun defines our cosmic neighborhood, carving a space of safety in an otherwise hostile galaxy. But one day, this balance will end. When the hydrogen in the core runs out, fusion there will stop. The outward pressure that has held gravity in check will falter. The core will shrink, heating up, while the outer layers swell and cool. This marks the beginning of the red giant phase, the death spiral of a star like ours. At first, the changes will be slow, spanning millions of years. The sun will grow larger, its light redder. The brightness will double, then triple. The inner planets will be scorched, their atmospheres stripped away. But deep inside, something remarkable will occur. As the core collapses, the temperature will rise high enough to ignite helium fusion. For a brief, brilliant moment, called the helium flash, the sun will surge with renewed energy. Helium will fuse into carbon and oxygen, giving the star a second life, shorter but intense. It will shine differently then, softer and redder, its heart remade by fire. But this reprieve will not last long. Helium burns faster than hydrogen, and after only a few 100 million years, that fuel too will be spent. The core will shrink again, this time beyond return. The outer layers will drift away, forming the glowing nebula that will mark the sun's farewell. The path from stability to collapse is written in physics, but also in poetry. The sun will not die suddenly. It will fade through stages of transformation, each one both destruction and renewal. The energy that once sustained life will return to the cosmos to become part of new stars and worlds yet unborn. Even now, every sunrise is a reminder of that process, a glimpse of eternity caught in motion. The light that warms our faces is the same light that billions of years from now will outshine our world's final hour. In the next part, we will journey forward again, into the far future of Earth itself, tracing the slow death of oceans, the loss of atmosphere, and the moment when our planet becomes uninhabitable long before the sun's final flame. Far in the future, the Earth will still circle the sun, but everything about that relationship will have changed. The light that now nurtures forests and oceans will have grown stronger, more merciless, more absolute. The sun will not yet have become a red giant, but even long before that final transformation, it will begin to undo the world it once created. It will start gently, almost imperceptibly. The sun's brightness will continue to rise, about 10% every billion years. At first, this change will be invisible to any single generation. Seasons will continue, tides will flow, days will pass as they always have. But over time, that extra light will accumulate, adding heat, transforming the air and the seas. In perhaps 500 million years, Earth's climate will begin to tilt toward instability. The extra warmth will intensify evaporation, drawing more water into the atmosphere. Clouds will thicken, storms will grow fiercer, and rainfall patterns will shift across continents. For a while, life will adapt, as it always has. Forests may creep toward the poles, deserts may widen, but the trend will not reverse. Each passing century will carry the planet closer to fever. As the atmosphere fills with water vapor, a strange effect will take hold. Water vapor is itself a greenhouse gas, trapping heat. The more it rises, the more warmth it holds, and the more it causes the oceans to evaporate. a feedback loop spiraling upward. Eventually, this process will trigger what scientists call a runaway greenhouse effect. When that happens, the oceans will begin to boil, not all at once, but steadily, relentlessly, for millions of years. Vast clouds of steam will rise, circling the planet in a bright haze. The sky will lose its familiar blue, replaced by a milky white glare. The seas will shrink, their surfaces scalding, their depths rising as vapor to the upper air. Rivers will dry, continents will crack, and what once was lush will become barren. Carbon dioxide will break down under the growing heat, removing one of the planet's key temperature regulators. Without that balance, Earth's thermostat will shatter. Long before the sun becomes a red giant, Earth's surface will already be lifeless. In perhaps 1 billion years, the last of the oceans will vanish entirely, boiled into space or broken apart by sunlight. Hydrogen atoms will escape into the void, leaving oxygen behind to react with the rocks. The atmosphere will thin, turning dry and thin as Mars's sky. The continents will glow under a relentless sun. The average temperature may climb above 200 degrees Celsius. Metals will soften, stones will melt, winds will scour the surface, carrying fine dust across plains that once held forests and cities. Life, as we know it, will not survive this transformation. Plants will perish first, unable to photosynthesize without carbon dioxide. With them will go the oxygen that fills our lungs. Animals will follow, first the large, then the small, then even the microscopic. Only a few extremophils, creatures of stone and salt and heat, might endure a little longer, deep underground or beneath the shrinking shadows of mountains. But even they will succumb as the planet's surface and subsurface temperatures climb. The biosphere, that thin film of life that has persisted for more than 3 billion years, will fade. For a time, perhaps, there will still be chemical traces of its presence. Fossils embedded in rock, the faint imprint of chlorophyll molecules trapped in ancient layers, but gradually even those will erode. Wind and heat will grind everything down. The Earth will become a silent world again. The continents will fuse into a single supercontinent, baked and cracked by heat. Volcanic activity will still occur, though the planet's mantle will slowly stiffen as its internal heat dissipates. Mountains will rise and fall into seas of molten rock. The surface will shine faintly red, like an ember cooled at the edges. From space, the planet will appear pale and brilliant, wrapped in thin layers of haze, a mirror reflecting the overpowering light of its star. The moon will have drifted farther away by then, its orbit widening as tides push it outward. Its familiar pull on the oceans will no longer matter, for the oceans will be gone. Yet, even as the Earth dies, the sun will still look beautiful. In the blackness of space, it will shine a little larger, a little whiter, casting long shadows across the desolate surface below. From the barren peaks of what was once a mountain range, a viewer, if one could exist, would see a sky stripped of clouds, filled with a sun that burns too bright to bear. At this stage, life may have found refuge elsewhere. Perhaps by then, descendants of humanity or other creatures that followed will have moved beyond the solar system, carrying the memory of their home star with them. The destruction of Earth will not erase the life it once hosted, only transform its story into light and motion, into a cosmic echo traveling forever outward. After the oceans vanish, the planet will continue to orbit the sun for another 4 billion years or so. But it will be a ghost, a dead world circling a brightening star. Every year the sunlight will increase. Every century more of the crust will melt. When the red giant phase finally begins, the transformation will complete what heat began, The atmosphere, long gone, will no longer protect the surface. Solar radiation will strike directly, breaking down whatever molecules remain. The once blue marble will be reduced to bare minerals and vapor. Eventually, the sun's expansion will swallow the orbit itself, either engulfing or vaporizing the planet entirely. This is the final irony. The same warmth that made life possible will be the force that ends it. The sun does not choose, it simply evolves, following the laws of fusion and time. From our perspective, it seems cruel, but to the universe, it is a natural rhythm. Even as the Earth dies, the elements that composed it will not be lost. They will drift into space, mixing with the sun's own expelled gases, becoming part of the interstellar medium that will someday form new stars and planets. The calcium of bones, the carbon of forests, the silicon of mountains, all will be recycled. In that sense, the death of the Earth is not the end, but a transformation, a return to the cosmic sea from which it was born. The sun will be both destroyer and creator, ending one world so that countless others might someday begin. In the next part, we will move beyond Earth, following what happens to the rest of the solar system as the sun grows, to Mars, to the gas giants, to the outer edges where the faintest traces of sunlight still reach. When the Earth is gone or transformed into molten stone, the story of the solar system will continue for a while longer. The sun's reach will keep extending outward, reshaping everything it once warmed. Even as the inner worlds vanish, the outer planets and their moons will face their own slow metamorphosis under the gaze of the expanding red giant. Mars will be next to feel the change. For now, it is cold, a desert of stone and rust, with polar ice made of carbon dioxide and traces of water. But as the sun swells and brightens, Mars will begin to thaw. Its frozen caps will vaporize, and for a brief, miraculous moment, the planet might become habitable again. Thin clouds could form, rivers might flow across valleys that have been dry for billions of years, and the surface could glisten with melting frost. If any remnants of life ever existed there, ancient microbes buried deep underground, they could awaken for a short golden age. The warmth that kills Earth might bring Mars to life, but it will be temporary. As the red giant grows larger, its heat will intensify far beyond what even Mars can endure. The atmosphere will be stripped away by solar wind, and the planet's surface will become an oven of dust and glass. Beyond Mars lies the realm of the giants, Jupiter, Saturn, Uranus, and Neptune. Worlds made mostly of hydrogen and helium will not melt or burn like rock. Instead, their thick atmospheres will react to the changing light in complex ways. Jupiter's upper clouds, normally tinted with ammonia and sulfur, will brighten and shimmer as sunlight grows stronger. The Great Red Spot, that enormous storm that has raged for centuries, may fade or vanish as heat stirs new patterns in the planet's endless winds. For a time, the increased energy from the sun might even ignite subtle chemical reactions in the outer atmospheres of these planets. Hazy rings of vapor, shimmering with new colors, could encircle them. The giant planets will become lanterns of reflected fire, glowing softly in the distant dusk. Their moons will change too, perhaps more dramatically than the planets themselves. Europa, Ganymede, Enceladus, Titan, worlds that now lie hidden beneath ice, will begin to thaw as the sun's heat reaches them. Beneath Europa's crust, the vast hidden ocean may rise to the surface, breaking through cracks and spreading in shimmering sheets. Geysers on Enceladus will erupt with greater power, filling space with plumes of steam. Titan's frozen lakes of methane will warm and evaporate, creating thick orange clouds. For a short while, maybe tens or hundreds of millions of years, The outer moons may become places of flowing liquid and soft light. They could host chemical reactions similar to those that once began life on Earth. These moments will be brief but spectacular, a final gift from a dying star. Jupiter and Saturn will remain massive enough to hold on to their atmospheres, but their systems of rings and moons will change. As sunlight intensifies, the icy rings of Saturn may darken and dissipate, the frozen particles melting and falling inward. The delicate geometry of orbits will shift as the sun loses mass and its gravity weakens. Moons will drift outward, their paths widening like ripples spreading from a fading source. Farther still, Uranus and Neptune will awaken from their long, cold silence. The faint sunlight that once reached them will grow 20 or 30 times stronger. Their skies will glow more vividly, their clouds stirred by energy they have not felt since the birth of the solar system. The deep blue of Neptune's atmosphere may become brighter, the strange greenish hue of Uranus more luminous. Even these distant giants will not escape the slow hand of change. In the Kuiper Belt, where icy bodies like Pluto and Eris drift, the faint warmth of the red giant sun will begin to melt frozen nitrogen and methane. For the first time in billions of years, their surfaces may soften. Thin atmospheres will form, then dissipate as solar winds increase. The far reaches of the solar system will briefly glimmer with reflection, icy plains shining like mirrors in the dying light. Comets, long frozen in the darkness of the Oort cloud, will be drawn inward. The red giant's gravity and radiation will send them streaming toward the inner system in bright trails. For millions of years, the solar system will be filled with comets, glowing tails crossing the sky, remnants of creation returning for the final act. But the red giant's breath will be deadly. The powerful solar wind will sweep outward, carrying away the sun's outer layers, eroding atmospheres, stripping moons and planets of gases. The heliosphere, the bubble of solar influence, will swell, reaching farther than ever before. The solar system will be filled with drifting material, dust, plasma, vaporized stone, and frozen gas. In time, the red giant will begin to pulsate. Its brightness will vary, its surface boiling and expanding in waves. Each pulse will throw off more matter, creating layers of glowing gas around it. The planets that remain will orbit through this haze, bathed in dim, reddish light. The night sky on any surviving moon or world will be filled with crimson auroras, reflections of the dying sun's fire. Eventually, the red giant will lose so much mass that its gravity weakens noticeably. The outer planets will drift even farther away, their orbits expanding into vast ellipses. Some may escape entirely, becoming rogue planets, wandering through interstellar space, carrying with them frozen echoes of the solar system's history. The moons of these distant worlds may freeze again as the sun begins to fade, their brief window of warmth closing forever. The moment of liquid water, of soft skies, will pass. What remains will be ice and shadow. When the red giant phase ends and the sun collapses into a white dwarf, the remaining planets will continue to orbit that small, dense star. Jupiter and Saturn, still immense and cold, will reflect its dim light faintly. The solar system will be a ghost of its former self, wide, dark, and quiet. From a distance, an observer would see a small white star surrounded by faint rings of gas and dust. A few planets, barely visible, would drift in the dark, illuminated by a light 1,000,000 times weaker than before. It will be beautiful in its silence, the final portrait of our sun's family, frozen at the end of time. But even then, change will continue. The white dwarf will cool, the remaining planets will wander, and collisions will still occur in the outer regions. Comets will still fall inward, and some may crash into the fading star, sending brief flares of light into the darkness. Even in death, the solar system will not be entirely still. In this slow decay, there's a kind of peace. The sun's violence will have passed, and what remains will be calm, a quiet structure of orbits, light, and memory. The fiery creation will end not with an explosion, but with a sigh. In the next part, we will move beyond the solar system itself to see how the death of stars like the sun fits into the larger life of the galaxy, and how, from their ashes, the universe continually rebuilds itself. The death of the sun, as vast and sorrowful as it may seem from our small perspective, is not unique. Across the galaxy, stars like ours are born, live, and die in the same slow rhythm, a cycle of light that repeats endlessly. Each one contributes to the tapestry of creation, turning death into renewal, destruction into beauty. The end of a star is not the end of its story. It is simply a change of form. Our sun is what astronomers call a main sequence star, ordinary, steady, long-lived, but when it becomes a white dwarf, it will join billions of others just like it. The Milky Way is filled with them, dim, ancient remnants of stars that once shone brightly, now cooling in silence. They are the fossils of the cosmos, glowing faintly among the spiraling arms. Yet, while stars like the sun fade quietly, others end in violence. The most massive stars, 10, 20, even 100 times the sun's mass, burn faster and die younger. In just a few million years, they exhaust their fuel and collapse under their own gravity, triggering supernova explosions that can outshine entire galaxies for a time. In that instant, they release elements forged in their cores: gold, silver, uranium, oxygen, carbon, scattering them into space. It is from those violent deaths that the building blocks of life arise: the iron in our blood, the calcium in our bones, the oxygen in our lungs. All of it was created in the heart of stars and dispersed by their death. The sun itself was born from that same kind of debris, a second-generation star formed from the ashes of giants. So when the sun finally dies, it will give back to the galaxy what it once received. The gases it sheds will mix with the interstellar medium, joining clouds of hydrogen and dust that wander between the stars. Over millions of years, those clouds will compress again under gravity, forming new stars, perhaps new planetary systems, perhaps new Earths. The light that destroyed our world will also give birth to others. This cycle is one of the most astonishing truths of the universe. Stars die so that new stars can live. Every end contributes to a beginning. The Milky Way itself is a vast ecosystem of light, constantly regenerating, constantly reshaping. Even as old stars fade, new ones ignite, and the spiral arms remain alive with motion and color. If we could see the galaxy from far above, it would resemble a great wheel of fire and dust. Dark lanes where cold gas gathers, bright clusters where new suns are being born. The light from these young stars illuminates nearby clouds, turning them into glowing nebulae of red and blue. Each nebula is both cradle and grave, containing the remnants of dead stars and the seeds of new ones. The sun's eventual planetary nebula will be one such light in the galactic night. For a few tens of thousands of years, it will shine with delicate filaments, expanding outward at tens of kilometers per second. From afar, it will appear as a colored ring, much like the famous Ring Nebula in Lyra or the Helix Nebula in Aquarius. In that brief, luminous span, the sun will make its last contribution to the galaxy's beauty. Eventually, the nebula will fade and blend into the interstellar medium, leaving only the white dwarf behind. It will orbit the galaxy quietly, one of billions of faint sparks circling the center. Over time, it will cool, becoming a black dwarf, a hypothetical object that, so far, does not yet exist anywhere in the universe because no white dwarf has had enough time to cool completely. When that happens, the sun's remains will be invisible, yet still present, a silent ember in the endless dark. The galaxy will continue without it. Stars will rise and fall, nebulae will form, disperse, and reform. Black holes will drift through the spiral arms, swallowing gas and light. In this grand cycle, the sun's life and death are neither tragedy nor triumph. They are a single note in an infinite song. On cosmic scales, even stars are temporary. The universe itself is evolving. Galaxies collide and merge. Dark energy drives them apart faster and faster, stretching the fabric of space. In tens of billions of years, even star formation will cease as the available hydrogen is used up. The galaxies will fade, leaving behind only remnants, white dwarfs, neutron stars, black holes. In that far future, when time has lost its meaning, the universe will be a place of silence. The stars will have burned out, the black holes will have evaporated, and only cold, dark matter will remain. Yet even then, the atoms forged in stars like the sun will still exist, scattered across eternity. In their tiny structures, the memory of light will endure. When we look at the sun today, we are not just seeing a star, we are seeing a link in that infinite chain, a bridge between what came before and what will follow. Its life connects us to the ancient stars that made our elements and to the unborn stars that will someday inherit them. We are part of its story as much as it is part of ours. If humanity, or whatever follows humanity, survives long enough, our descendants may travel to other stars, carrying with them the memory of the sun. They might look up at alien skies and remember the gentle warmth of their original star, long extinguished but never forgotten. The sun's death will not end its influence. Its story will live in memory, in matter, and in the continuing rhythm of the universe. Perhaps one day, on a world far from here, someone will look at their own star and wonder how it began, how it will end, and what it means to live in its light. And in that thought, in that act of wondering, the sun will live again. In the next part, we will bring the story home, tracing what this cosmic cycle means for us, for life, and for the strange beauty of impermanence that defines everything under the stars. To think about the end of the sun is to think about the end of everything we know. The warmth that wakes the oceans, the light that nourishes every leaf, the glow that paints each dawn and sunset. All of it comes from that single star. It has been constant, patient, and forgiving. And yet, like every star, it carries its death inside it from the moment of its birth. The story of the sun is not only a scientific one, it is a mirror of existence itself. Life and death are not opposites. They are partners in the same cosmic rhythm. The same process that will one day destroy Earth is the process that made it possible in the first place. That paradox, that creation and destruction are the same act, is written into the physics of stars and the poetry of life. If we look at the sun as more than just an object of fusion and gravity, we begin to see it as something larger, a symbol of persistence, of change, of the unstoppable flow of time. It has burned for nearly 5 billion years, and through that fire, every living thing on Earth has drawn its existence. The light that falls on your skin today began in the sun's core tens of thousands of years ago, trapped in a dance of atoms before finally escaping into the void. It traveled across space and found you, a single photon carrying warmth and history. To understand the sun's end is also to understand our place in time. Humanity has existed for only a blink in the sun's lifespan, a few 100,000 years out of billions. Civilizations rise and fall faster than a solar flare. Entire epochs of our history are less than a flicker on the sun's surface. Yet within that brief window, we have learned to look up, to measure, to wonder, to know that one day the same light we revere will consume us. There is a strange comfort in that knowledge. The sun's destruction is inevitable, but it is also far beyond our reach, billions of years away. Long before it happens, we will have had time to evolve, to move, to change, perhaps even to escape its grasp. The end of the sun reminds us that permanence is an illusion, but continuity, the passing on of life, of knowledge, of curiosity, is real. When we gaze at the sun, we see our origins. Its atoms are our atoms. The carbon in every living being was once part of a dying star. The sunlight that warms the earth powers the chemistry of thought. The fusion that will one day end our world is the same process that fuels our existence. It is the most profound connection imaginable. We are made of the same fire that will one day take us back. The ancient peoples of Earth understood this intuitively long before they had words for fusion or gravity. They worshiped the sun as a god, as the source of life and time. They marked its rising and setting, built temples aligned with its path, and structured their calendars around its cycles. Even then, they sensed that to understand the sun was to understand everything. Modern science has replaced myth with measurement, but the reverence remains. Astronomers studying stellar evolution are not unlike ancient priests watching for omens in the sky. They too are reading the language of light, trying to understand the will of the cosmos. And what they find is humbling. The universe is neither cruel nor kind, only vast and governed by laws that give rise to both beauty and impermanence. The sun will die because it must. The laws of thermodynamics are unyielding. Energy flows from order to disorder, from fusion to cooling, from creation to decay. In that slow transformation lies the truth of everything, that all things change, and that change itself is the source of all meaning. If the sun were eternal, there would be no urgency, no evolution, no striving. Life exists precisely because the sun changes. Its light drives adaptation. Its variability shapes climate. Its eventual death compels us to look beyond our world. Mortality, on every scale, is the engine of creation. When Earth's oceans boil and its sky fades, it will not be a punishment. It will be the natural end of a long story, the closing of a chapter that began with a spark in a cloud of dust. The atoms of the sea, the air, the mountains, and every living thing will scatter back into space where they will wait for the next act. In that sense, the Earth's death will be an act of generosity, a returning of borrowed materials to the universe that lent them. It is possible that by then life, or something descended from it, will have left Earth behind. Perhaps it will travel to other stars, carrying the memory of the sun as an ancestral flame. Perhaps it will find other worlds warmed by other suns, repeating the pattern in infinite variations. The end of one star does not end the dream of life. It only moves it to new skies. Imagine a far future being, human or otherwise, standing on another world beneath another sun. They might look up at the night and see a faint, tiny point of light, the remnant of our sun, now a white dwarf cooling in the dark. They might not know its history, but its photons will still travel outward, bearing silent testimony to a world that once existed. In that light, even extinction becomes connection. The sun will give back what it has taken, not as destruction, but as transformation. It will scatter us into the wider cosmos, and in that scattering lies immortality. This is what astronomy ultimately teaches, that we are temporary but not meaningless. Our transience is part of the universe's design. To know that the sun will die is not despair, it is awareness. It means we live in a moment of light between two eternities of darkness, a moment that allows us to see, to think, to feel, to be. In the deep future, when the last ember fades, there will still be memory, not in minds, but in matter. The atoms that once made sunlight will still exist, spread across the cold expanse, waiting for the next beginning. Somewhere, a new cloud of gas will collapse, a new star will ignite, and once again, the universe will shine. In the next and final part, we will step back one last time to see how this cycle of birth and death, of stars and life, reveals the deeper poetry of existence, how from darkness comes light, and from endings, infinite beginnings. There will come a time when the sun no longer shines, no warmth, no dawn, no rays breaking over the curve of a world, only the quiet presence of what once was, a dense white ember fading into invisibility. The solar system will have become a shadow of its former self, a collection of frozen planets orbiting a silent star. The story that began in fire will end in stillness. And yet, even in that stillness, there is beauty. The sun's long life, its birth from dust, its steady burning, its final transformation is not a tragedy, but a masterpiece of balance. Every stage has its purpose. Every end has a reason. In the same way that a leaf falls to feed the soil, the sun will give itself back to the galaxy that made it. Its light will have traveled billions of light years by then, reaching corners of the universe it never knew. Photons from the sun that left long before its death will still be flying outward, carrying with them the story of Earth, the reflections of oceans, the colors of forests, the glint of human cities. Those beams of light are already spreading through space, a cosmic message written in silence. We were here. To imagine the end of the sun is to imagine the end of time as we know it. But time itself will continue. New stars will form, born from the remnants of the old. New planets will circle them. Some will be barren, others fertile. Somewhere, another world will grow forests and seas. Somewhere, other beings may lift their eyes to a star and wonder how long its light will last. They will not know our names, but they will know our story, not through words, but through atoms. The hydrogen of our oceans, the calcium of our bones, the carbon of our breath will have become part of new worlds. Life, in some distant form, will remember us not by history, but by chemistry. We will live again in the veins of other creatures, in the air of other skies, in the light of other suns. That is the quiet promise of the cosmos. Nothing is ever truly lost. Matter and energy change form, but they endure. The fire that made us will someday burn elsewhere, reshaped and reborn. Our sun's death will not be a sudden darkness, but a slow fading. It will pass through colors, from gold to red to pale blue-white, before vanishing into black. Billions of years later, even as a black dwarf, it will remain, invisible but still massive, still part of the Milky Way's endless rotation. Around it, the frozen remains of planets will continue to orbit in silence, tracing the paths they have followed since the dawn of time. If one could stand in that future, in the place where Earth once was, the view would be haunting. There would be no light but the faint glow of distant stars, no sound but the motion of dust through space. And yet, through that emptiness, there would be peace, the kind of peace that comes when everything has completed its journey. Perhaps by then, the galaxy itself will be changed beyond recognition. The spiral arms will have blurred, the stars scattered, the night thick with darkness. But even so, in that darkness, the memory of light will persist. Every particle, every atom, every photon will carry the echo of creation. For us, here and now, the sun still burns in its youth. It rises each morning, steady and golden, keeping the rhythm of life on this small world. Its light touches every ocean, every leaf, every living thing. And though we know that one day it will fade, that knowledge only deepens its beauty. The impermanence of the sun and of everything is what makes each moment precious. To live beneath a mortal star is to live in wonder. It means to be aware of fragility, yet to love fiercely anyway. It means to know that our time, like the sun's, is limited, and that this limitation gives life its meaning. Every sunrise is a beginning, every sunset a reminder. The same cycle that governs the star also governs us: birth, growth, decay, transformation. We are reflections of the universe, shaped by its laws, luminous for a time, then returning to the whole. When the sun finally dies, there will be no mourning in the cosmos. The universe does not grieve, it continues. But through us, through thought, through art, through wonder, the universe becomes aware of itself. Every human who has looked at the sun, every creature that has felt its warmth, has participated in something eternal. Even as the sun fades, its story will be complete, and complete stories never truly end. They become part of everything else. So, in the grand silence of the future, when light is gone and the stars are only memories, what remains will be this: balance, beauty, and the simple truth that from endings come beginnings. The same laws that will extinguish the sun will ignite others. The same matter that made our world will build new ones. The cycle continues, as it always has, as it always will. We are not separate from that cycle. We are it. The sun's fire burns in our veins. Its light pulses in our thoughts. When it finally goes dark, we will already have become its legacy, scattered across space, living as starlight in another form. And so the story of the sun and of Earth ends not in destruction, but in transformation. The end of light is not the end of meaning. It is the beginning of everything that comes next. The stars will keep rising somewhere in someone else's sky, and their light will carry forward the oldest truth the universe has ever told, that nothing lasts forever, and that is precisely why it matters.